Hello everyone, welcome to Mana CS Classroom. Today we are going to learn about optimization of basic blocks and DAG representation. So before starting, let me tell you a small story. Suppose your mother asks you to bring milk, bread. After some time, again she asks you to bring milk, eggs. Milk again. What will happen? You will say, Amma milk already తెచ్చాను కదా ఎందుకు మళ్ళీ Exactly the same problem occurs in programs. Many computations are never used and some computations are repeated unnecessarily. Some statements can be simplified. Compiler tries to remove all these inefficiencies. This process is called code optimization. Today we will learn how a compiler optimizes a basic block using a special structure called DAG. So optimization of basic blocks. In previous videos we learned basic blocks. Now the compiler wants to improve efficiency of this basic block. Optimization performed inside a single basic block is called local optimization, and optimization across multiple basic blocks is called global optimization. So two type of optimizations, local optimization and global optimization. If we perform optimization inside a single basic block, then that is known as local optimization, and if we perform optimization across the multiple basic blocks, then that is known as global optimization. Now we shall see how this optimization is important and what special structure, as I mentioned earlier, what special structure is used and how to construct that special structure. Okay, so why this optimization is important? Because it reduces the execution time if we eliminate or if we remove unnecessary instructions, repeated computations, and it reduces the memory usage also, and we don't need to compute an expression again and again. Okay, it reduces the redundancy, and so that its performance will be improved. So that is why this optimization is very important. Optimization means improving the program without changing its output. Okay, the answer produced by the program remains same, only efficiency improves. So what is DAG? It stands for directed acyclic graph. Directed means it shows some orientations, it contains some arrows which have direction, and acyclic means no cycles exist, and it is a graph which shows the flow of the execution. So how to construct this DAG and how this DAG helps us in optimizing a basic block? So mainly the advantages of DAG are it helps us in eliminating common sub-expressions, the expressions which are already have been computed, and dead code elimination. Sometimes some instructions are unreachable. Control never execute them. So dead code elimination and statement reordering, some algebraic simplifications. So this DAG helps us in doing all this: elimination of sub-expression, elimination of dead codes, and algebraic simplification. So how to construct this DAG? So DAG is not just a picture. It helps the compiler discover optimization opportunities, possibilities. Repeated calculations can be removed, unused calculations can be removed, expressions can be simplified. So how to construct this graph? First, create a node for every variable appearing in the basic block. Whichever variable appears in the basic block, create a node for those variables. These nodes represent initial values. For example, if there is a variable A, if there is a variable B, then create a node for these initial values, for these variables as initial values. And rule number 2, for every assignment involving an operator, create a new node as an internal node, and its children are the nodes representing the operands. Suppose if there is a statement x is equal to y operator z, then we need to create y. As I told you, for every variable we need to create a node, right? So Obviously, we should have created Y node and Z node. Now I am telling you how to create an internal node. So which operator is placed in between these two, that node is to be created as an internal node, and children nodes are Y and Z. And this operator is to be labeled with the X. It is to be named as X because the result is being stored into X. So it is to be labeled as the node X. So this is how you draw a DAG for a given expression. Okay. First you create nodes for the variables, which are nothing but operands on the right side, and these two are to be connected with an operator which is placed in between Y and Z. And that node, internal node, if you notice a small point here, I have encircled the internal node, not the external nodes. Okay, so we need to leave the external nodes. We need to circle the internal nodes, and they are to be labeled with the left hand side variable where we are storing the result. In this example, in this statement, we are storing the result into X, right? So we need to label that internal node as X. So that is how we need to construct a DAG for. If we see this example, the example which is being shown on the screen, T1 is equal to A plus B. So with our previous discussion, what we understood, first we need to draw nodes for A and B, because they are the variables and they are the operands on the right side. And then we need to draw an internal node with the operator placed in between those two operands. Here in this case, the operator placed is plus. So you need to draw an internal node for plus and encircle it because it is an internal node. And where are you storing the result? What is the variable present on the left side of is equal to T1, right? So you need to label this node with the name T1. So this is how you draw a DAG, directed acyclic graph, for a given expression. So this kind of expressions, you may have many expressions in a single basic block. So you need to draw this kind of DAGs and you need to combine all those graphs consecutively. You will get a graph. So as we already mentioned, label the node with the operator. Okay, so suppose if you see here, so I'll show you how DAG helps in finding the subexpressions or how to create a DAG when two expressions are given. See, first expression is A plus B. So first I am drawing the nodes A and B, and these two are to be connected with the operator plus, and it is to be labeled with T1. And then the next one is T1 star D. So already the expression T1 is computed and a node is labeled with the name T1. This node we need to use, this value we need to use for the computation of next expression, the second expression. And the operator in the second expression is multiplication operator, and you are storing the result of the second expression in the variable C. So you need to encircle the second operator node and label it with the name C. So this is how we draw the DAG. And next, what do we mean by output nodes and what are the variables live on exit? Okay, so some variables are needed after leaving the basic block. That means suppose if I have three basic blocks, B1, B2, B3. If I am talking about B1 basic block, if a variable is needed after leaving B1, in B2 and B3 also I may need that variable. That kind of variables are known as live variables. Variables which are needed after leaving a basic block are known as live variables. Their corresponding nodes are marked as output nodes. So suppose I have B1 basic block. Okay, so as I am leaving B1, whichever variables I may need in the future, those variables are to be marked as output nodes, okay, or output variables or output nodes. So they are known as live variables, okay. On the exit of B1, if this is B1, on the exit of B1, they are the live variables. For example, A, I may need this variable A in B2 as well as B3, okay, let us assume. So that kind of such variables are known as live variables, okay, the variables which are live on exit of a basic block, and they are known as output nodes, okay. Before leaving or on the exit of B1, I am marking A as the output node. That means I may need A in the future in further basic blocks also. So they are known as live variables, okay. Now we shall see a complete DAG example with the two expressions. Let us build the DAG step by step. So as we have the first statement, A is equal to B plus C. So here I'll create node for B and C, and I'll draw an internal node with the operator which is present in between B and C, which is nothing but plus, and I'll label this plus as A, okay. And then second instruction, in second instruction I have E, the variable E. Whatever value I have computed in the first expression, I am using that latest value, right? So this is not the older value, this is the latest A, this is latest A which has been computed in the first expression. That I must use here, okay, that I take it and I'll combine it with the operator present in between A and E, which is nothing but minus, and this minus I'll label it as the variable which is present on the left side of this is equal to of the second instruction, that is nothing but D. So this is how we create DAG, okay. So now the graph represents all computations inside the basic block. What are the advantages of this DAG? Once the DAG is built, optimization becomes much easier. Compiler can easily detect inefficiencies and generate better target code. Okay, so advantages are it removes repeated calculations, removes unused calculations, it simplifies expressions, better code generation. Okay, so today we learned what is a DAG and how to construct DAG, and what are the rules to construct a DAG, and how it helps us in the optimization of a basic block, means advantages of DAG. Okay, so in the next video we will see how the compiler becomes intelligent enough to reuse previous results and remove useless code. If this video helped you, please like, share and subscribe to Mana CS Classroom. Thank you.